Hello and welcome everyone to the Quimper Geological Society event. We are so glad to have you all here. Yes, we were listening to the stylings of the Vitamin String Quartet there, and that last song was a Billy Joel cover of the song We Didn't Start the Fire, and I thought that was appropriate to kick off Jen's presentation and to start thinking about the topic of fire. My name is Rebekah Korenowsky, and I am the Education and Engagement Manager for Jefferson Land Trust. And we are so proud of the Quimper Geological Society and are happy to help present these online events. Michael and I are very excited to bring you this talk. Just a couple of items up at the top here related to our platform. So we are in a Zoom large meeting, and you are very welcome to turn on your cameras to show up for Jen as the audience, so she has some visual on who she is presenting to throughout the event. If you're experiencing issue with your connection, however, I would recommend turning the video off, as that will free up some of your bandwidth so you can receive more of the information on the screen. Similarly, we will have the audience mics turned off for the duration of the presentation, and Michael and I will be working together towards the end. Oh my gosh, I'm laughing so hard at Jen saying hi, Mom, in the chat. Hello to Jen's mom, honored guest, welcome. Parents are always welcome at these kinds of things. Yes, so Michael and I will be working together towards the end of the presentation to set up a little Q&A with Jen. And so we will be doing all of those questions through the chat. And so if you're not familiar with Zoom, on the bottom part of your screen in roughly the center, if you are on a computer, there will be an icon that looks like a speech bubble. And if you click on that, you'll be able to send a chat to everyone, and that's where we'll ask that those questions go. So share those with everyone so we can all benefit from the ideas that are stirring in your own head. We will be recording this presentation and it will be available to the Quimper Geological Society after the event via a link, and I believe Jen is planning on sharing this with some of her students and other folks as well. So if you enjoy the presentation and want to share it with someone else later, do look out for a follow-up, and you can always head to the Quimper Geological Society website, quimpergeology.org, to check out our events that we've recorded previously in this series. I will turn on the option for closed captioning, and you are able to turn on and off this closed captioning option. So if you go into the bottom of your screen, again, if you are on a computer, or if you tap on your screen and go to the menu, if you are on a tablet or device, you can choose to have the closed captioning on or off. And I will point out that proper nouns are very difficult for this service to live transcribe. So down at the bottom of your screen, there will be an icon, 2 C's in a white box. And if you click on the up arrow next to that, you can tell it to turn on or off the subtitles. Similarly, if you click on the More button, if you are on a tablet or phone. And this is just so anyone who is in need of that extra access is able to participate in our events. And please do send me messages in the chat if you need any assistance with that. As far as timing goes, we will try to wrap up at about 5 with the presentation, with the Q&A to follow. But please do send questions into the chat here anytime. I'm going to just send you one so you can all see where that comes. So we'll start here like we start most of our events with a poll. And this is just an opportunity for us to get to know you a little bit better. So we have 2 questions for you here at the start. Where are you from and what is your background? And so you'll need to answer both and click submit in order to share the results with us. And once we get, a critical mass of answers in on this poll, I will end that and share it with you all so you can all see who's here participating as well. We'll be interested to know if you have an other answer, especially to the what is your background question. If you would like to share with us in the chat what your background either with climate science or with geology or fire science is, or something completely different, that's okay too. So we've got about 80% people reporting. So I'll give it just another moment and then I'll share the answers with you. We've got someone in law, someone in geography, a wildlife biology, environmental biology focus. So there's a range of people in the audience here today, and it's all related, of course. Okay, I will end the poll, and if you miss it, go ahead and type that in the chat. And Michael, no surprise, Port Townsend, QGS headquarters, coming in at 40%. And then actually the largest contingent of folks in our audience is no geology or climate or fire science background. So folks are here to learn something new. That's awesome. Thank you all for being here. So I'll stop sharing those results and I will pass it over to Michael Machette to welcome in our presenter. Hey, Michael.
Hi. Hey, everybody. Looks like we've got a Canadian lurking out there somewhere, someone from outside the United States. Maybe it's a German, I don't really know. Anyway, thanks for coming today. It's the last speaker for our spring series, and we'll start again in October. I think we have mass extinctions, alpine glaciation, and a comparison of South American and Mount St. Helens volcanoes. Anyway, we have a good lineup. It's not quite gelled yet. We're going to have a couple field trips this summer, a series of them. There'll be beach walks both at Nodule Point and Marrowstone, and then beach walks in the North Beach, Fort Worden area. And these are informal sort of things, but they go on half a day or so. We'll have a formal field trip in the fall at going to the Ottawa River with Ian Miller to look at the removal of the dams, the reservoir bottoms that are being revegetated, and then the development and extension of the Elwha Delta into the Straits of San Juan de Fuca. That'll be in September sometime. Other than that, I think you just stay watching the website and you'll see what we've got developing through time. Today's speaker, as we mentioned, is Jen Pierce. I've known Jen for all of her life probably, and a good part of mine. She's considerably younger than the average person here. She's a professor at the Boise State. She's a professor at Boise State University in the Department of Geosciences, where she's been since 2005. She grew up in Colorado in the Golden area, spent her summers in the mountains of Western Wyoming, probably a formative event, I suspect. She received her undergraduate degree from the Colorado College in Colorado Springs, went on to get her master's degree from the University of Oregon, and then finished up with her PhD at the University of New Mexico. So she's well educated, as you can see, just like her former geology relatives, which I'll mention at the end. She currently serves on the board of directors for the Friends of the Teton River. Her research and professional interests include wildfires, landscape response, soils and carbon storage, climate science, education and outreach, and building diverse leaderships in the geosciences. Jen she received the 2018 Boise State College of Arts and Science Faculty Excellence Awards. So they're recognizing her teaching abilities. And she's the founder of the Idaho Climate Literacy Education Engagement and Research Network. And she was recently named a fellow of the Geological Society of America, which is kind of a big deal. That was in 2020. When she's not working, she enjoys mountain biking, backpacking and country skiing, backcountry skiing, playing music, and exploring the outdoors with her family and dog. And did I mention, I think I did, she's a third generation geologist. Her father and grandfather were both geologists. So all I can say is good luck to your daughters. So without further ado, I'd like to turn it over to Jen. She's going to speak about fire, climate, and erosion today. Jen?
Thank you so much for that wonderful introduction, Michael. And it's a great pleasure to be here talking to some folks who I know and quite a few folks who I don't. And so thank you so much for taking time out of your Saturday. I really also want to thank Rebekah for her wonderful hospitality and the intro music. I'm a big fan of intro music, and so I really enjoyed that. So thank you. For all of you who are not geologists or fire scientists, I'll be presenting quite a bit of material here today, and some of it may be geared at the right level and some of it may not, and I just really encourage questions. So I'm going to try to get through this so we have plenty of time to ask and answer questions. So my talk today is on wildfires, climate, and erosion in the past, present, and future. So big topic right there. My motivation for this is manyfold. In following the music theme and the talking heads, you know, this is not my beautiful house. This is not my beautiful wife. This is a really pretty chilling picture, right, from the campfire about recent fires in the Western U.S. and devastating loss of life, property, and our forested and sagebrush steppe landscapes due to fire. So how did we get here? What you'll hear often on the news and other places is, you know, the reason we have and we're experiencing such large standard placing fires is because we suppressed fires in the past during the Smokey Bear era of the 70s, 60s, and that buildup of fuels is what is causing these large catastrophic fires now. And I think that that is potentially part of the answer, but I think we need a lot more information. So that's really my motivation, is to really understand what's driving our fires today. And to answer that, really, we need to go back in time. So my questions for today, first we'll kind of go through what is the, what do we know? What are the known knowns, in the words of Donald Rumsfeld, about fires in our landscapes today? Then we'll talk a bit more about post-fire landscape response, talk a bit more about fire as an agent of erosion. For the science geeks in the audience, we can talk a little bit about the mechanics of runoff generated erosion and recent work from some of my students. And then we will go back in time and talk about changes in fire regimes over short and long timescales, and hopefully add a little bit more information to that question of what is driving our fires. Is it climate or management? So to frame this, I have a figure that I modified from Kathy Whitlock, the fire triangle, where here we have climate governing what I call geomorphic response to fires. So this would be erosion and sedimentation. How does the landscape respond to wildfires? Changes in vegetation. So of course, over longer time scales, for example, going from glacial to interglacial intervals, our landscapes and our vegetation in our landscapes responds to that changes in climate. But then, of course, following a fire, we have a dramatic response of vegetation when it gets burned up with respect to that fire-driven change in vegetation on the landscape. So these are all the types of things I'll be talking about today. So we'll be going quickly from Fire Science 101, and this is something that one of my current students, Danielle Marquette, is developing for 4th grade to 6th grade students in our Idaho schools to better understand how fires work through hands-on experiments. As I'm sure you all know, if you don't have fuel, oxygen, or heat, and ignition isn't kind of included in that heat component, you will not have a fire. What I'd call Fire Science 301. Fires burn when a fire burns over longer and larger areas. When you go from the origin of the fire on the scale of seconds to days, then over the scale of days, topography will influence fire behavior. As you go to the scale of decades and longer, then we have what are called fire regimes. So I may be referring to this in the talk. So fire regimes are kind of the fire behavior over decades and longer within a certain vegetation type or certain landscape. Over thousands of years, so what I'd call Fire Science 501, fires can fundamentally alter rates and processes of erosion. And this is really a growing area of interest in the geomorphic and geologic community, something we call pyrogeomorphology. How important are fires to our landscapes? Also, over again, thousands of years, our vegetation adapts to certain fire regimes, and the fire regimes reflect those certain types of vegetation. So how does fire actually really control what trees and other shrubs, etc., invasive grasses recently that we see on our landscapes? Okay, so again, going now to our known knowns of fire now. So we're going to start with our modern era. This is a really important paper by John Abasaglu and Park Williams, where they demonstrate that human-caused climate change has caused over half of the documented increases in fuel aridity since the 1970s and has doubled the cumulative forest fire area since 1984. So very profound findings here, and this is echoed by quite a few other publications showing that human-caused climate change causing over half of the documented increases in fuel aridity. This might be a video that maybe some of you have seen, but it's worth repeating from NASA, showing our global changes in temperature. And you can see the years down there in the bottom, 1800s. The warmer colors are warming temperatures. These are from measurements. So there's no debate about these measurements. As we go into the 50s and 60s, this again is our Smokey Bear era. And we were good at putting out fires when it was relatively cool and wet. Mid-1980s, major change. We're really starting to see warmer temperatures globally. These correspond with increased lengths of the fire season, melting of our ice caps, etc. So great video from NASA, and there's actually an updated version. I keep going, there we go. So this is not the primary point of this talk, but I did want to bring up this really important point. This is from the Yale Climate Communications Center, really great website with lots of great information that I recommend check out. Estimated percentage of adults who discuss global warming at least occasionally. This is as of 2018. These blue colors indicate that most people don't talk about it. Okay, so climate change, global warming is something that, because of various reasons, has fallen off our list of things that we often talk about. I would encourage you to try to bring this up every day with your friends, with back in the days pre-COVID, with your Uber driver, with someone in the checkout line, For example, right now here in Boise, Idaho, we are getting much needed rain. It has been a very dry spring, and we are looking at a very dry summer. And I'm quite worried about the fire activity we're going to experience out here. This relates to something called the SASSY quiz. And so if you're taking notes or just want to remember this, if you Google Yale SASSY quiz, this will come up. These are the six, what are called the 6 Americas. And this is a graph that just came out today that I got in my email inbox from the Yale Climate Communications Center, showing that the percentage of Americans who are alarmed about climate change is growing. And this is, I think, something that needs to happen. The folks who are either doubtful or dismissive of climate change is staying relatively static, but perhaps is changing a little bit. So I would encourage you to check that out. I asked Michael if we could do it during the talk, and he thought that might be too distracting. So do it on your own time and let me know what your results are. Because I have 2 kids and I am worried about their future, I'm worried about my future, I've started something called iClear, the Idaho Climate Literacy Education Engagement and Research Group. And I'm sure there are other similar groups in your area. So lots of ways to get engaged. And I've been doing a lot of work on K through 12 outreach, which I'd be happy to talk about at the end of the talk. So how does this relate to fires? Well, I often joke with people that I went to school for 12 years after high school to tell you this. You all ready? Okay, it's profound. All right. What I learned in those 12 years of schooling is that forests burn when it's hot and dry. I know, groundbreaking. But it turns out it's true. And it's true even when we look back over longer time scales. And that's a big part of what I'm going to be talking about today. So if we're talking about our mixed conifer dense forests, they burn when it is hot and dry. Anyone who has tried to start a campfire when it is cool and wet can attest to the fact that forests are just not going to burn when it's cool and wet. For many of the folks in the audience out in Port Townsend and the surrounding areas, you know this very well. And so this is certainly not news to you. For those of us who spend time in our Western rangelands, rangelands are a different story. Rangelands, and so here I'm talking about what used to be in many areas our native sagebrush steppe, those burn when we add fuel. We've added fuel in the form of cheatgrass and other invasives since really the mid 1800s is when cheatgrass got introduced. So cheatgrass, so fuel and ignitions from human ignitions are really changing fire regimes in our rangelands or our sagebrush steppe. So those are examples of 2 dramatically different ecosystems where we cannot compare fire regimes between forests and sagebrush steppe. So very ecologically dependent. All right, other known knowns. It turns out that with increasing temperatures, the number of lightning strikes in the US could increase by about 12% for every degree Celsius of warming. So as it gets warmer, we will actually experience more natural fire ignitions in the form of lightning. Another known, humans start an awful lot of fires. In the US, human-started wildfires account for 84% of all fires in the US. That has tripled the length of the fire season and now is dominating an area 7 times greater than that affected by lightning fires. And my joke here, New Year's resolutions, seek help from my pyromania. This is certainly something we as people can do something about. We have also extended the length of the fire season. So again, with those warmer temperatures and human ignitions, this is a human started fire outside of the Jackson area in Wyoming. It was a warming fire that got out of control. We have extended the length of the fire season really on both ends. This is a figure from a former student of mine, Mel Kunkel, showing that the timing of snowmelt in Idaho's watersheds is getting earlier and earlier. So as snow melts off our landscapes earlier, our fuels dry out. This combined with human ignitions, often in the fall, where we wouldn't see as many of those natural ignitions, is really extending our fire season. I wanted to highlight this recent paper from another colleague of mine at Boise State, Moji Segda, in the conversation, and I'll try to put a link to this in the chat. He and his co-authors do a great job of summarizing our upcoming fire season. So I encourage you to check that out. In particular, for the greater Yellowstone area, and for certainly for Utah, we are looking at likely a significant wildfire season in July and August. For you out in Washington, it's more in Eastern Washington that will really take hold. Another figure from the paper from Mel Kunkel and myself, climate variability also really contributes to fire, increased probabilities of fire. This also makes sense if you have a year, let's see, last year where it was relatively wet, we didn't have that many fires in Idaho. That has built up fuels for this season when it will be drier and likely have a more severe fire season. So climate variability also contributes to fire activity. Getting back to those human ignitions have extended the fire season throughout the year. And so here we can see the number of fires, and this shows the number of percent human ignitions in red. And this really shows those human ignitions are dominating in the eastern US, whereas more natural ignitions dominate in our mountainous areas. And I think we can all potentially identify this spike in human ignitions right here, corresponding with a certain date. And you can type that into the chat if you have figured out what it is. So again, our human ignitions are really extending our fire seasons throughout the year, whereas our natural ignitions really are limited to the summer. Winds. It turns out that climate change can also affect the winds that are driving fires. Climate models predict that more intense Santa Ana wind events are on the way, and that the total area at risk of being burned by Santa Ana fires by mid-century could increase by 60%. So of course, this is limited more to the California area, but winds are the wild card in terms of fire behavior. So just some take-home points then. So rising temperatures due to human-caused climate change have doubled the cumulative forest fire area since 1984. More ignitions mean more fires, and humans account for 84% of all wildfires in the US. Longer fire seasons mean more fires. So again, snow melting off our landscape earlier in the spring, and then often again, those human ignitions extending our fire season in the fall when we are sustaining those warmer temperatures. And finally, more wind can result in more severe wildfires. So that is a kind of a glimpse of the current drivers of fire on our landscapes today. Now we're going to take a little breath and move our minds back in time. So now we're going to think about climate, fire, and erosion over both recent timescales and Holocene timescales. So by the Holocene, I'm talking about the past about 10,000 years in the Western US. So I'll return to those burning questions. So first, we're going to talk about post-fire landscape response. How important is fire as an agent of erosion? I'll talk a little bit about, yes, Virginia, there are run generated flows. And this is something that was believed couldn't happen from a physical standpoint until enough people said, well, they are happening, so we better figure out how and why. Advances in techniques, and this is really work from one of my former students, Nick Ellett. And then we'll get into a number of studies that document changes in these fire regimes over longer timescales. So, okay, first of all, we'll talk about these different types of geomorphic response to fire. So again, this landscape response to fire. And here I want to point out these two kind of types of geomorphic responses to fire. So we've got, I'm looking at my little, see if I've got my little arrow thing. The first one is what we call runoff generated events. So runoff generated events typically happen soon after fires, so the season after fire, where reduced infiltration on recently burned hill slopes. And this reduced infiltration is due to fire-induced hydrophobicity, so that burn soil surfaces are actually water repellent. And also because of surface sealing effects of ash and other material. These combined effects don't allow water to infiltrate into the soil, and instead it runs off and creates these rills. As rills progress down hill slopes, they add more and more sediment from that top layer, and then can produce what are called fire-related debris flows or floods. Second type of response to fire typically occurs within 2 to 10 years following a fire, after you get root decay on burned landscapes. So once you have lost that tree canopy, and once the roots have decayed in the subsurface, you've lost both the interception from the trees and the cohesion from those roots that would stabilize those burned hill slopes. So this promotes what are called saturation-induced failures. That's where you have saturation of the subsurface, you have water in that pore space, again, reduction in cohesion and stabilizing forces, and these can also lead to very large debris flows. And if people can see my arrow cursor down here, you can see a person down here for scale in this very large saturation-induced failure. We studied this erosional response to fire following the Pioneer Fire in Idaho of 2016. This is a very large fire in Idaho. Here are my daughters when they were a couple of years younger. If they were here, they'd be very embarrassed about this photo. But and they're playing with this very water repellent ashy material on these recently burned slopes in the Pioneer Fire. Here's my former student, Nick Ellett, and his master's thesis really focused on quantifying erosion from a watershed burned in the Pioneer Fire. Nick, when he got to Boise State, said he was really interested in this technique called structure for motion. And I said, I don't have any idea what you're talking about. What is structure for motion? And he said, well, you can fly a drone around and take a bunch of pictures, and you can actually measure changes in elevation, for example, on hill slopes. And I said, go for it. That sounds great. And so Nick really was the brains behind his project. There he is with his quadcopter, and he documented erosion in a small watershed that was burned in the Pioneer Fire. And this is really something that is kind of at the forefront of pyrogeomorphology, really trying to understand how material is eroded from the hill slopes. So this is what he found. He found that that debris flow scour from this channel was responsible for about 3,500 cubic meters of sediment delivery. So about 3,500 cubic meters of debris flow scour in the channel. And this was measured from a DEM of difference that he constructed using structure from motion from this, what I like to think of as poor man's LIDAR, which is a real boon in technology for post-fire erosional studies. And this work is also published in Earth Surface Processes and Landforms in 2019, if you want to check it out. Nick was also able to measure erosion from hill slope rills. And so he estimated about 1,100 cubic meters of material eroded from these rills. Again, the structure from motion really was a groundbreaking technology, whereas in the past, you can imagine if you had to go out, and rills are these just tiny, tiny, tiny little gullies, and measure erosion from, you know, maybe thousands of these. He's able to estimate this with structure from motion. This is even more interesting because when I first started going to the American Geophysical Union meetings, or AGU, in the late 1990s, early 2000s, it was believed by the physicists that runoff generation wasn't possible. And so I was actually told this by some geophysicists, well, you may think you have observed runoff generation after fire, but it's just not possible. And I would hold up pictures and I'd say, well, how do you account for this then? And I think this really documents a lot of great new work and great new papers in this area. So here's a couple of examples of runoff generated debris flows here from the North Fork, Boise, here from Nick's study area, where you can see this fresh recent debris flow deposit following the Pioneer Fire. And these are some examples of some of the folks who are at the forefront of this research, really adding to our understanding of post-fire erosion. Many of these folks are also with the USGS, and it was quite remarkable that here is the USGS has developed a really fantastic post-fire debris flow predictive hazard model. The USGS predicted from their model that about 4,900 cubic meters of material would be generated from this watershed that Nick examined right here, outlined in black. And the amount of sediment that we measured was 4,600 cubic meters. That's pretty darn good. So hats off to the USGS folks and their debris flow predictive model. So I want to think a little bit more longer term. So we certainly have documented that fires are very important to erosion on short times. How important are they on longer time scales? So here we can see Nick's study from the structure from motion study. And we're going to compare that now with the longer term estimate erosion. So short-term erosion rates vary from, in this case, about 6,000 cubic meters. And this is now, we're translating this into thousands of years, to other studies that were done with Grant Meyer and myself of about 44,000 tons per square kilometer. So very substantial erosion from these single events. Background rates of erosion without fire are much lower. So below typically about 10 millimeters per 1,000 years. When we look at the Holocene average of erosion, and these were estimated from some radiocarbon dates, from some beryllium-10 dates, we can see that these longer term averages are a mixture of short-term sediment fluxes without fire and the occasional but very important sediment inputs from fire. So I think the take home from this is, and you can look at Fred Swanson, a big name in your area of sediment yield, is that we have a base flow sediment yield, kind of like a hydrograph without fire. And then we have this fire accelerated sediment yields, where fire really is contributing the largest and very important amount of sediment to our systems. Now, this whole time we have been talking about water. We've been talking about erosion following fire from post-fire debris flows and post-fire floods. Now I'm going to shift gears a little bit to prior work from another student, Clay Roner, where he documented post-fire erosion from wind. This is very important in our rangeland ecosystems. This is this image is from the 2015 Soda Fire, and this really kind of hits you over the head when you see these wind drifts of not just sediment but carbon on landscapes following fire. So Clay's work is also published 2020, Earth Surface Processes in Landforms. And so here he is with his Home Depot bucket out setting out dust traps. And I know Zara is out there, one of my current students, and Carrie, and we'll be setting up dust traps just like this out in Kimberly, Idaho next week. So Clay actually measured dust fall following fire. And what he saw was that wind erosion is a very important agent of pyrogeomorphic change in our rangeland ecosystems, not just in terms of sediment, but again, in terms of carbon. And down at the bottom of this slide, you can see those sample trays showing kind of our typical small rates of dust deposition without fire and post-fire deposition. So we have coarser sediments, we have more organic sediments, and we have a lot more sediment following fire. This really only lasts for until the first growing season. So from our observations following the Soda Fire, and this is out in the Reynolds Creek Critical Zone Observatory in right on the border of Oregon and Idaho. Again, what Clay's results show are a mass flux increase post-fire, grain size increased. Geochemical results, and that's what this chart is showing, also show a local geochemical signature, so that more material is being transported locally, just from hill slope to hill slope, versus more of a regional geochemical signature from non-post-fire dust. This gets into some other really interesting questions in terms of longer-term hill slope evolution. In our part of the world, and perhaps yours as well, the winds blow from the southwest to the northeast. So over time, if we have after fires, increased transport of dust and organics from the windward slopes on the southwest to the leeward slopes on the northeast, this may contribute to something else that a former PhD student of mine, Mike Polis, documented, showing that our north-facing slopes have thicker and finer grained soils than do our south-facing slopes. So some really interesting bigger picture points here. A lot on this slide, but what I really want you all to remember is that wind is also an important agent of geomorphic change following fires. All right. So those are our modern fires. Now we're going to use that information that we have just learned from our modern fires to help inform records of longer term erosion following fire. So here again, we're talking about the last 10,000 years and getting into what I would call Fire Science 501, that over thousands of years, we're really thinking about these long-term interactions among climate, vegetation, erosion, and fire. So my former students and Grant Meyer down at University of New Mexico, who was my PhD advisor, and his students have now compiled a pretty large data set of fires in the Western United States. And we have quite a few take-home points in this study, and I'm looking at the time. So I'll see how many of these I can get through. So now we're going to look again at these longer-term records of fire and climate. The areas we're looking at, unfortunately, we don't have records from your part of the world out in the Port Townsend area. But we do have quite a few records from the Northern Rockies and from Southern Colorado and New Mexico. So that's what I'll be now talking about, is the summary of those results. These are records of fires reconstructed using charcoal fragments from a variety of ecosystems. So we have our higher elevation mixed conifer forests that typically burn in infrequent but stand replacing fires. We have our mid-elevation ponderosa pine to Douglas fir forests, which have a variety of fire regimes, which I'll talk about in a minute. They burn both in frequent but low intensity fires and in infrequent but stand replacing fires. And then finally, we have some records from our lower elevation sagebrush steppe. So how are we reconstructing these fires? These are our primary methods. It's looking at records from alluvial fan deposits and collecting charcoal fragments from those deposits. So the charcoal is important for two reasons. First, because it shows us that there was a fire, right? So if we find abundant fragments of charcoal, we can say, gosh, this is a fire-related deposit. The second reason charcoal is important is that you can date it. You can use radiocarbon dating to actually reconstruct the timing of those fires over time. So this image here shows a stratigraphic sequence from Carrie Riley's work on the Middle Fork salmon in the Frank Church Wilderness of No Return in central Idaho. So this is one of, gosh, 50 to 70 different alluvial fans that Carrie examined for her thesis work. She dug them out with a shovel and painstakingly collected charcoal samples and described the stratigraphy from, again, 50 to 70 alluvial fans. So from this, you can see for this one example, we have multiple dates in this fan. Not only that, but we have different types of deposits. We have sheet flood deposits at the bottom and towards the top. And we have a really thick debris flow deposit here in the middle. So this is important because actually the type of sedimentation following fire can give us clues to both the vegetation type and to the burn severity. We compared these records of fire with other independent records of vegetation change. So this is Kathy Whitlock, and she cored this lake right behind us, Decker Lake, and reconstructed vegetation change from that lake. I and my students also analyzed charcoal macrofossils to try to determine at least whether it was pines or fir or riparian vegetation that burned. And we also had a really neat project at City of Rocks with Julio Betancourt, and this is actually his son, Mark, collecting samples from pack rat middens, which also gave us good vegetation reconstructions over time. This is a really busy figure, and I'm not expecting any of you to be able to see it, for one thing, especially if you're watching this on your phone. But wanted to point out, these are the sum of all those radiocarbon dates from all those different study areas going back in time. This is 10,000 years. So by summing up all those radiocarbon ages, comparing them from different study areas, now we can have an idea of changes in fire activity over longer timescales. I'd like to acknowledge that this is the decreased number of dates that you see that are older does not mean necessarily there were fewer fires, but this is an artifact likely of the fading record. So which is harder to find more fragments back in time. So what do these tell us? First, that ponderosa pine and Doug fir forests burn at what I would call both ends of the spectrum. So this is my work and Grant Meyer's work from the South Fork Payette and the Yellowstone area from 2004. And what we're showing here are a couple things. This blue line, so if you look at the top figure, figure A, you can see that when we look at the erosional response from those fires, we see a peak in small events, small sheet flooding events in the Payette Ponderosa during a time what's called the Little Ice Age. So this is a time characterized by generally cooler and wetter climates than today. It was also characterized by frequent low intensity fires in the Payette Ponderosa. And this is what most of the time you think about as being what should be experienced in our Payette Ponderosa. So this gets back to that first question I asked at the beginning of this presentation. Are we experiencing these large standard placing fires now because we suppressed fires in the past? That's really was the point of this study, was to try to better understand that by going back in time prior to very active management. Now, some of you in the audience might say, well, what about Native American burning, and how might that have controlled fires in these areas? That is a great question. From what we know, though, of the South Fork Payette, there was very limited Native American fire management in this area. This is different from places, for example, like the Willamette Valley, where we know that there was active Native American fire management in those areas. So what we can hypothesize is that this then is this natural fire signal. Frequent low intensity fires in the Payette Ponderosa during relatively cool, wet times. Now let's compare this with the record from Yellowstone National Park. This is Grant Meyer's work, Yellowstone, which is shown in gray. There were not fires in the Yellowstone high elevation mixed conifer forests during cool, wet times. And this, for anyone who has visited Yellowstone, will not be hard for you to imagine. This is generally cool, wet. It is hard to get a fire to burn until it gets warm and dry, like it did in 1988. When we look back in the past, we see peaks in both the Yellowstone mixed conifer forest and in the Payette Ponderosa during a time called the medieval climatic anomaly. This is a time when it was extremely warm, dry, and variable in both Yellowstone and in Idaho. This is a time when we see severe fires, catastrophic meaning large, and extraordinary fires in both of those ecosystems. So even without management effects, we see large fires when it is warm and dry. Again, my somewhat obvious take-home point there. And again, this is a time when we, prior to fire suppression. So that was not what was governing those large fires back then. This is supported from records from New Mexico. And showing you here, and this is Aaron Fitch's work, records of both sheet flood deposits and thick debris flow deposits. So again, the nature of that geomorphic response can tell us something about the burn severity in that basin. Thinking back to Nick Ellett's work with structure from motion, if you have a extensive severe fire within a basin, that typically will produce a large erosional response. If you have a patchy moderate fire, that produces a minimal erosional response. So again, that is what we're seeing back in time. Not only does that erosional response vary with the severity of the fire, but it also varies with the type of ecosystem, where if you are in a rangeland, less densely forested area, you typically get a less of an erosional response than from a forested area that only burns occasionally. So part of this is that buildup of sediment on those hill slopes. And I'm going to keep going quickly because I've got 5 minutes. This is Carrie Riley's work from 2015. Again, thinking about those sediment yields over longer time scales. What she found was that, again, this is a semi-log scale, that we have very, very large erosional responses from upper basins that were previously forested. And in fact, when we look at the comparison of this fire-related sediment to the overall Salmon River sediment yields, this indicates that these episodic fires are really responsible for a lion's share of the sediment to the overall salmon river. And this is something I'd like to continue working on. Summary side from Carrie Wepner's work at the City of Rocks, to kind of sum this up, our conceptual model is that when we have a wetter climate with higher vegetation density, this leads to higher slope stability, increased soil development, increased sediment storage on those hill slopes. Then if those hill slopes burn, you have a large erosional response. We have just lost that vegetation. We have these larger debris flows. In drier climates, you have lower vegetation density. These are more prone to sheet flooding, less soil development, less sediment storage. Following fire, then we have a decreased erosional response. Okay, moving quickly through this segment. The vegetation on these landscapes has not always been as we see it today. Something really, I think, super cool to think about next time you go out in the woods. It turns out that in the Northern Rockies, our pines, our ponderosa pine, our lodgepole pine, our pinyon pine, are all relative newcomers. They've really only arrived in about the last 4,000 years. And this is shown from those charcoal macrofossils and that pack rat midden evidence. So generally with the pines comes an increase in fire activity. Can't actually resolve with the resolution of the radiocarbon dating, but did the fires come first and therefore kind of pave the way for pine colonization? Or did the pines come first and promote kind of more increased fire activity? So that was all talking about our forests. In our sagebrush steppe, these landscapes used to be fuel limited. This means that they were limited by a lack of fuel. You just had one sagebrush to the other with maybe some flowers in between. Since the arrival of invasive grasses, in particular cheatgrass, and human ignitions, we have completely changed fire in our sagebrush steppe landscapes. They are now fires less than 100,000 acres used to be unheard of in these ecosystems. Now fires over 100,000 acres are a frequent occurrence. This is an image of the Soda fire again in 2015, over 280,000 acres and not fuel limited. Our moist high elevation forests burn infrequently during times of drought. So again, this is our kind of typical image of a high elevation dense mixed conifer forest, which typically burn infrequently. So 300 to 400 up in your neck of the woods in the Olympics, and even 500, 600, 700 years from Dan Gavin's work. Very infrequently, but in large fires. Past records, and I'm going to kind of skim through this, do show some times of synchronous activity. Again, particularly about 900 years ago during the medieval climatic anomaly, about 500 years ago. So there are times when we see synchronous fires from the northern Idaho sites to New Mexico. But really, that doesn't compare to what we have seen in recent decades, where severe fires have burned at least 8 of the 10 sites examined in this study. So it's hard, though, to compare those records, the records from radiocarbon to records from satellites. So challenges for the future: we need to understand the role of climate change, land use, and prior management, and better quantify the future of fire on our landscapes. And of course, this overlaps with development in what I'd call the fire plane in our wilderburbs that are particularly fire prone. Couple of notes to leave you with. Again, back to John Obotsoglu and Park Williams' work, that anthropogenic warming has caused over half of the documented increases in fuel aridity and doubled the cumulative forest fire area since 1984. So can we even use these older records? Or are we in a no analog situation now? More fires means more sediment. I'd point you to Joel Sankey and Jason Kreitler's work from GRL, also showing that 1/3 of our watersheds are projected to increase by sediment yields by over 100% by 2041. excuse me, this could have some major ramifications for our water storage in our watersheds and in our reservoirs. And finally, wanted to point to Jen Marlin's work, and she's actually one of the main investigators for the Yale Climate Communications Project. Her other hat is as a fire ecologist and climate modeler, showing that prior to fire suppression, activities such as grazing really may have contributed to a fire deficit. So on our landscapes. So not saying that land use did not have an effect, but I think that it's pretty complicated. So fire suppression in the 50s to 80s and grazing in the late 1800s has undoubtedly contributed to this fire deficit in low severity fires. But really what we're seeing and what is affecting our lungs and our communities is an increase in severe large stand replacing fires in areas which have not burned in our memory. So thank you very much for listening to this presentation and for inviting me, Michael, who I knew as Mike, Machette, and Rebekah to your wonderful group. So thank you very much, and I'll be happy to answer any questions. Applause, says Rebekah.
Okay, thanks, Jennifer. That was a fascinating tour of fires, climate, and erosion. I knew almost none of that, even though I was a geomorphologist once. We have a half a dozen questions or so that have come up, and I'm expecting some more will come along as we talk here. But let me ask you a few of these and see what you think. First question was, could you speak more about the implications of grain size sorting on northern slopes?
That's a great question. So there are multiple influences. So what Mike Pullis and others, quite a few other researchers have observed in the Dry Creek experimental watershed right outside of Boise is that our north-facing slopes have thicker soils, finer grained soils, and more organic matter than our south-facing slopes. So of course, our north-facing slopes, because of the tilt of the earth, receive less insulation and are cooler and wetter. And the vegetation differences on north versus south-facing slopes in our neck of the woods are pretty striking, where the trees, the forested slopes are on the north-facing slopes and sagebrush steppe on the south-facing slopes. So the grain size question is multifaceted. I think that there are a couple different reasons for that. First of all, you are getting preferential both deposition and trapping of loess, which is our silt-sized grains on our north-facing slopes because of the direction of the wind and because that vegetation traps the loess. The other factor, though, is that you have more extensive weathering on north-facing slopes, which will break down rocks into finer-sized particles. So we don't know really how much of that grain size difference is due to more loess, or less is more, or to increased weathering on our north-facing slopes. So really good question.
Okay, thanks. Another one, and I think this was posted just as you were talking about it. Have you seen any evidence of Native Americans using fire as an environmental tool like it's been demonstrated in Australia?
Again, I think that's a really important question. And this is where you have to be, you cannot extrapolate results from, say, I could not take my results from the Idaho Ponderosa, even potentially to the Ponderosa outside of Bend, because that Native American signal could have been different. In the Payette area, what the archaeologists tell us and other groups, these were really the sheep eater populations of Indians were not doing, or Native Americans were not doing much fire management. They were mostly following sheep and not managing for agriculture. The Willamette Valley is a completely different story. The other thing in Idaho is we're not ignition limited. We have plenty of lightning. So if it's dry, we will have plenty of lightning to start fires. Other places like the Willamette Valley are ignition limited. you don't have many natural lightning strikes. So that's an area where, especially in xeric kind of summer dry conditions, Native American fire starts really can make a big difference in how what our landscape was like. And of course, they were also using fire as a management tool. So really good question.
Okay, I think this is Will Smothers. I can't really tell from the chat, but he asks, what preceded the pines, I presume, in tree vegetation more than 4,000 years ago?
That's another great question. Doug Fir. Doug Fir is the big daddy on these landscapes. It appears that Doug Fir has been around. It was here before the pines. And so that we see those macrofossil midden and other evidence of fir. In other places, for example, the City of Rocks, there we had our kind of our last glacial holdovers of white bark pine, our 5-needle pine from glacial conditions. And so you're seeing this kind of slower vegetation response as these ecosystems come out of the last glacial, and our pines kind of march up from the south. So
Thank you. Paul Bellinger out there says, just a FYI for you and us, a drought monitor that has historical tracking comparisons as well as simply weekly tracking, and he gives the website URL for it in the chat room there. So
oh, awesome. Yes, that's a great, that is a great website. Thank you for putting that in there.
At UNL, I think, yeah. Steve McDivitt says, thanks. We all thank you. It looks like aquatic ecosystems are going to see big impacts. How catastrophic will be for the salmon river drainage?
That's a great question, Steve. And it's interesting. So the fires on a longer time scale in the middle fork of the salmon, and I wish Russ Thoreau was here because he's a salmon biologist there. But what he and Minshaw and others, Colden Baxter at ISU, have found is that for the greater ecosystem, those fire-related debris flows actually are good for the fish in that they provide the size of spawning gravels that they need, and kind of those mobile spawning gravels that the salmon need to spawn. Of course, as you can see behind me in my picture, for whatever drainage burned and had the debris flow coming down it, that's game over for whatever fish were there. But on the bigger salmon scale, fires can actually be beneficial. It also changes in productivity, because if you burn riparian areas, then you have more sunlight, and so it's a hard one to answer, but really good question.
Okay, and I think our final question here from Chip Barnett. Is there any data on fire risk related to transmission line corridors over their history and those that cross a variety of terrains? That's got California written all over it. But
it sure does. And obviously, as we've seen from California, our power transmission lines and that form of human ignitions can be devastating, right? So Idaho is certainly, I think all states now after California are very aware of this. And I don't have data on my fingertips. I think though what this also points to, and the fires 3 years ago in Hood River that I'm sure you all heard about or were aware of, that for the transmission lines, this question of, okay, how big of a buffer do we need? And alarmingly, of course, as we saw after the fireworks starts in Hood River area, that fire jumped the Columbia River, which is a mile wide at that section. So our management tools in terms of fire breaks then would need to be a lot bigger than we might want to think. So.
okay. Well, I don't see any other coming up, but I want to thank you. for using your afternoon to educate us about fire, climate, and erosion. And if everybody could give her a virtual clap, we'd appreciate it.
Absolutely. Thank you so much for inviting me. And I'm trying to put my email into the chat and I'll be happy to stick around informally and answer any questions if folks would like. So
Great. Thank you very much.
thank you. Thank you so much for coming.
We'll see you guys in the fall in October for some kind of a talk.
Thanks for coming, Justin.
Have a great evening. Take care.